I know what you're thinking. You might be thinking, oh, it's so pretty. Or you might thinking, oh, we're so little, like we're nothing in the galaxy. But what I'm thinking is actually, how can we catch those stars? I think this problem is not if, I think it's how do we do it. So just to clarify, I'm not actually like having a big nest, like go grab a star and like bring it back to Earth. But like we're trying to create a star and maintain it on Earth. So stars like our sun have used fusion, nuclear fusion to produce energy. And that's how they give out sunlight and the heat. So they actually use hydrogen as a fuel to burn, but their extreme pressure, extreme heat actually pressure these electrons and protons to split. And when they split, the protons are always positive, the electrons are negative. But protons will fuse together under extreme heat and the extreme movement speed. So then, when they fuse together, the hydrogen protons actually make helium-3 or helium-4, and sun cheat on making this because sun's internal gravitational pull actually is naturally creating those pressure and in turn creating heat in their core. But how can we build a star on Earth? It's a completely different story. On Earth, we do not have any of those super pressure and then super high heat, but what we can do is to get smart. So scientists noticed that the lowest temperature that we need to create fusion is actually 150 million degrees Celsius. That's like a crazy, insane temperature. Imagine you're boiling water, it's only 100 degrees Celsius, but this is 150 million. That's 10 times hotter than the sun's core, than the natural environment that fusion is gonna occur in. So scientists get smart again. They're like, okay, so should we still use the hydrogen atoms that we used before, or should we use something else? Well, they found out that using deuterium and tritium actually will produce faster reaction rate in a slower energy needed. And the mechanism is basically deuterium and tritium's protons meet together, fuse together for 3 or 4 times, and then make helium-3 or helium-4. But then actually the result of helium-3 and helium-4 has a lower mass than the beginning protons and neutrons. And that different in mass actually are released in the form of energy. But where can we find deuterium and tritium? Is it really that abundant on Earth where we can just like find it everywhere? Actually, we can find deuterium everywhere. We can distill it from most form of water on Earth, especially abundant in oceans, salt water too. But where can we find tritium? That's a bit tricky. There's only an estimate of 20 kilograms of tritium on Earth, and they're mostly found on nuclear warheads. So that makes it super expensive and super hard to find. Well, scientists got smart again. The scientists changed, they said, oh, tritium doesn't work, then why don't we try other stuff? So they substitute with helium-3, and helium-3 is actually really abundant on the moon. So if we can go to the moon and then go mine those helium-3 and bring them back, then we can probably do nuclear fusion pretty easily, and it's really abundant source. So nuclear fusion, this core is actually called plasma, and the superheated deuterium and tritium form ionized gas and form plasma, which is superheated matter. and this is what they look like in the fusion machines. The plasma is actually really abundant. Like we can see it everywhere in the universe, just not on Earth. Plasma actually glows in the night sky as form of stars, nebulas, and even auroras on both poles of Earth, which is so pretty and crazy, and it made up 99% of the universe. So that's like the core technology of fusion, but plasma are superheated to 150 million degrees Celsius. Finding a bottle to bottle that star is really tricky, because what machine is gonna hold like that hot matter and control it, maintain it, heat it, and then make it provide energy for us? So scientists from the largest fusion experimental facility in the world called JET actually made a machine called tokamak. From Russian, it means the donut-shaped magnetic machine. So in this machine, plasma will flow around, and both sides of the machine will have a magnetic field going around and pressuring all those electrons in the machine to move faster and faster. And there will be electric current moving around both sides of the machine as well to heat the matter. And then trying to make the protons fuse together and create energy. Then the energy as the heat will be absorbed from the liquid metal all around the machine and used to heat water, turn turbines, and change it to electricity. And scientists in the National Ignition Facility use a different approach to induce nuclear fusion. And what they use is actually this machine called Horon, which all those names are so super weird. I guess they're trying to get fancy. And then it's actually the use of laser beams and ion beams to shoot at this one little point at the same time and heat it to extreme heat of 150 million degrees. And that's like the inside of NIF's machine. In this case, they actually use 192 laser beams and shoot a single point, a beam-sized pellet, at the same time to induce fusion. So this kind of fusion is what I call force fusion. Force fusion can only be alive for 1/1,000,000th of a second, which is super short amount of time. You don't even feel it, but the output energy is actually 50 to 100 times the input energy, which is crazy. Now, anything have both sides. I can't just say one side of the problem, be like, oh, fusion's gonna solve a problem. Fusion's gonna be like everything. But fusion have downsides too. So in the process of fusion, tritium gas will actually, small amount of tritium gas will actually be released into the air. And when that meet with the oxygen in the water, it will produce radioactive water, which is really harmful for the environment, and it can diffuse into the ocean to harm the marine life. But that's like one of the downsides of nuclear fusion. If you ask my opinion on it, I would say nuclear fusion would solve the problem of energy shortage in the world and maybe help solve climate change. And what about the danger of nuclear energy? Like what we heard is like nuclear fission, like death, leakage, Japan, like all radioactive waste. But it actually is so much safer than traditional way of burning coal and oil. And there's only one death in 1,000 kilowatts hour, and there's only 0 death in nuclear fusion every 1,000 kilowatts hour. So I think nuclear fusion can be the answer to our climate crisis and energy shortage crisis around the world. And I wish that nuclear fusion could light up every home around the world on Earth, and maybe light up this home and provide the electricity for them to properly live their life.